So today is going to be our second talk on sunflowers. And really the goal of today is going to be to prepare the ground for getting an improved bound for sunflowers using this tool called the spread lemma that we're going to see today and we're going to prove tomorrow. So let me remind you what we did yesterday. So we defined the sunflowers. Let me just remind you quickly of the definition, because if you miss this definition, it's sort of it's really hard to follow what's going on. So a sunflower, so an R sunflower, is a family of R sets. This is sets S1 to SR, distinct sets, such that if we denote by K their common intersection, I from 1 to R, then except for this common intersection, they are pairwise disjoint. So that S1 minus K up to SR minus K are pairwise disjoint. So again, that maybe is a picture. No. This will be the common intersection. That will be one set, second set, a third set, and so on. And like I told you, R denotes the number of sets in the sunflower, and the first non-trivial case is R equal to 3. So I really encourage you to think about R equal to 3 from now on, because that's going to already encompass all of the complexity of the problem. And again, we define this Ramsey parameter SFNR, which is a maximal size of a family F of n sets. To remind you, an n set is a set of size n that does not contain an R sunflower. Right, and the main goal is to try to prove bounds, lower and upper bounds, on this Ramsey quantity. What's the largest size of a family of sets of size n that does not contain this specific pattern, an R sunflower? And we've seen several bounds yesterday. We've seen, for example, a construction showing that this is at least R minus 1 to the n. So it is at least exponential in n. So if you think as R as constant and n as large, this is at least exponential in n. We've also seen an upper bound that gives a similar looking bound, but there's an n factorial factor here, R minus 1 to the n. And again, this was what we call the sunflower lemma. So this was proven by Erdos and Rado in the 60s. And again, the main gap here is if you think of R as constant, either this scales like an exponential to the n, and this scales roughly like n to the n. So the base here is n and not a constant. And that was the main question. Do you need this extra n factorial factor here? And the sunflower conjecture here, so the relevant conjecture here, the sunflower conjecture, was that you don't need it. That SF and R is at most some constant to the n, where the constant can depend on R, but is independent of n. Because that's the main conjecture in the area. And what we're going to see today, is not how to solve this conjecture. This is still open, but how to make progress towards this conjecture. So the theorem that I want to tell you about, and we're going to see a full proof of it today and tomorrow, is that you can get an improved bound, which is at most some constant R log n to the n. So this is an absolute constant. I think like 100 would be fine, but let's put C here. And again, so the R to the n scales more or less like we have the lower bound scaling. And the main improvement here is instead of getting n to the n, we get log n to the n. So we improve the base from n to log n. Okay? So that's our goal, to prove this. And the way that we're going to prove it is actually by trying to relate it to something that seems completely unrelated, which is probabilistic processes. Okay, so now we're going to See, we get all of that today. And I think a good way to start seeing, how you might try to improve on the sunflower lemma is I'm going to show you a reproof of the sunflower lemma, but with a slightly different viewpoint. And with this new viewpoint, it's going to become more evident, like what are we not using about this problem? What else can we use to try to get a better bound? So let me give you another proof of the sunflower lemma. So we're going to get the same bound as the one we saw yesterday, but with a slightly different proof. So again, let F be a family of n sets that without an R sunflower. And now we're going to define a parameter k, which is going to be R minus 1 times n. And you'll see why this parameter is natural in a minute. And we're going to ask ourselves a question. Is there an element in our universe that is popular? Popular means it belongs to at least a 1 over k fraction of the sets. So we're going to ask either an element x that belongs to, let's do if it's, to at least 1 over k fraction of the sets. And we're going to do a case analysis. We're going to prove it if the answer is yes, and we're going to prove if the answer is no. Okay? But that's going to be our inflection point. So let's first assume that the answer is yes. So case 1. So assume there exists some element x that is in 1 over k fraction of sets. Okay, I'm going to continue over there. So let's define f prime to be, we're going to take all the sets in our family that contain this element x, and we're going to remove it. We're going to s minus x. Okay, we just remove this element from them. And we'll say, well, what is this f prime? F prime is a family of n minus 1 sets. And then claim it also is without an R sunflower. Why is it without an R sunflower? Because if I could find a sunflower inside f prime, I could add x back to the sets and get a sunflower inside the original set f. So if S1 prime up to SR prime in f prime R and R sunflower, then, if I add back into them S1, which is S1 prime union X, up to SR, which is SR prime. If I add back X to them, then they are inside F, and they are in R sunflower, which is SF for sunflower. Right? So this is the inductive case. If there's an element that's very popular, we can just remove it, keep all of these sets, and then get sunflower. Why? Because now by induction, we know that the size of f prime is at most, r minus 1 to the n minus 1 times n minus 1 factorial. And we said that this element x is popular, so the size of f is at most this parameter k that we said times f factorial, f prime. Right? K was a popularity measurement. And then we said, well, we chose k such that exactly what we get here is what we're hoping to get, r minus 1 to to the n factorial. This is why we chose k to be, r minus 1 times n. So this is one case. This is a structural case, an inductive case. There is some structure in my set system. In this case, the structure is a popular element. And we use this structure to apply induction, right, to reduce to a simple case. The other case is you can think of it as an unstructured case, or maybe the pseudo-random case, when there is no popular element. So now we need to do something different. Right now we cannot use structure anymore. So case 2, no element is in at least 1 over k fraction of sets. So in this case, we want to say that our set system has some random-looking behavior. Concretely, what we're going to prove here is that F contains our pairwise disjoint sets. Okay? Which in particular form an R sunflower with an empty kernel. So how do we prove it? We're just going to do counting, right? So let S1 up to Sm be maximal number of pairwise disjoint sets in F. And let's assume that M is at most R minus 1. Otherwise, we're done. We found R disjoint sets. So in this case, I want to prove to you that there has to be an element that belongs. It cannot be that all the elements are in less than 1 over k fraction of sets. Why? Let's say we take A to be the union of Si. And let's ask how many sets intersect A. Or let's say okay. So wait. So the size of A, each set has size n. There are at most R minus 1 sets. So this is at most R minus 1 n, which is how we set up K. Now I'm claiming that if you have a set of size K, and every element sees less than 1 over K fraction of sets, there has to be another set disjoint from S1 up to Sm. So this cannot be maximal. So just see why. So let's see. So let's ask, let's count sets in F that are disjoint from A. And we'll do it in a very naive way. This is going to be at least with the number of sets in F minus, we're summing over all elements X in A and asking how many sets in F contain X as a member. Right? This is a very naive sort of, counting. And we said by assumption, this is less than 1 over K times F, because we said there is no popular element. And the size of A is K. Everything is a size less than 1 over K, so this is positive, right? So it cannot be that M is maximal, so that S1 up to Sm are pairwise disjoint. There has to be another set disjoint from one of them, and we can find our sunflower this way. So again, this is the same proof we saw yesterday, just presented in a different way. We're identifying this property of whether there's a popular element, and we're asking, is there a popular element in our set system or not? If there is, we're using induction. And if there is not, then we say, well, we can prove directly that there are pairwise disjoint sets. Okay. But now that once that we saw it in such a way, then sort of it's natural to ask, like, why just look on a single element? Why not ask if there are 2 elements that are popular, or 3 elements, or 4 elements, right? So that's going to lead us into a definition that's trying to identify when there are popular elements and when there are no popular even sets of elements. Okay? So this is, okay. So that's going to be our goal now. So we've seen this proof. We've seen this proof relies on having a single element that's popular or not. And we're going to try to generalize this definition to more than one element. So now I want to make 2 very important definitions. The first definition is going to be of something we're going to call a link. So let F be a family of sets. Let T be some set, not necessarily in F. So the link of F at T is the following thing. So Ft, denoted by F subscript T. So we're going to take all sets in F that contain T as a subset, and we're going to remove it. We're going to take it's going to be S minus T. All right, so for example, if my sets are, let's just do an example, 1, 2, 3, that's one set, and let's say 1, 4, and let's say 2, 5. Let's say this is my set system. Then F, if I look on the link of, I don't know, 1, it's going to be, let's take all the sets containing 1. In this case, it's going to be 1, 4, and 1, 2, 3. This one we're not going to take, and we remove 1. So it's going to be the set containing 4 and the set of 2, 3. Okay. So this is the link. So it's like if you have a graph, it's like the neighborhood of a node. Or if you have a hypergraph, it's a neighborhood of a node or a set of nodes. Okay? Definition is clear? Good. Notice, by the way, in the proof here, we looked on links of single elements. Right? We looked on a single element, and we asked how many sets are there in the link of a single element? How many sets contain this one element? Okay. But now I want to extend beyond a single element. Okay. So the second important definition is going to be that of spreadness. So again, let F be a family of sets, and let K, at least one, be some parameter. We say that F is K spread if for all sets T, if I look on the link Ft, it shrinks down. So it's most K to the minus T times the side of F. Good. So let's look at this definition for a second. So what does it mean that it is K spread? It means that every element is in at most a 1 over K fraction of sets. And every pair of elements is in at most 1 over K squared. And every 3 is 1 over K cubed, and so on. So this gives us a much stronger notion of pseudo-randomness compared to just having a single element not being very popular. Okay? And really, what's going to be the main idea? We'll say, well, if my family is not K spread for some parameter K, then we could basically use induction. We could go to a link that's still large and prove something there. So this is going to then move all of our focus into studying the structure of spread families. And the hope is that because now we're going to restrict in not just a single element of being too popular, but every subset of elements of being too popular, and the popularity decreases exponentially with the size of the number of elements in the set, maybe we could get better parameters. Maybe we can still prove that such a spread family contains many disjoint sets. So that's going to be, in fact, what we're going to do. Okay, so maybe let's start with the simple thing. The simple thing is, let's just see why we can just reduce to the case where the families are spread. This is just going to be basically using induction. Let's just sort of get this out of the way. Okay, so it's going to be basically this lemma, capturing it. So let's say let some n and r be some parameter, n, r, and k be some parameters, and assume that any family F of, let's say, n prime sets, where n prime is something at most n, which is K spread, contains an R sunflower. Then we can bound this parameter SFNR bar at most k to the n. Okay, let's go through this lemma again. We said if we could prove a good bound on sunflowers for spread families. In fact, if we could prove that being spread enough guarantees having a sunflower, then we can do it for all families, basically by induction. So let's just see how do we prove it. Right? The whole point of this, and from now on, once we prove this lemma, we can just focus on spread families because the structural case is easy to handle. So let's see. So there are two cases. So if F is K spread, then we are done, right? We can just apply our assumption. So let's assume not. Okay. Continue here. So if the family is not K-spread, by definition, there exists a non-empty set T such that this link is pretty big. Ft is at least the size of F over K to the T, right? This is not being K-spread, right? You have a large link. But then basically we just apply induction to this, right? Then we can say, well, basically, now by induction, so now basically we can apply induction. And here is where we use the fact that we need an assumption not just for n, but for all sets smaller than n, which is just some technicality. Basically, apply induction. We get that, the size of Ft is at most k to the n minus t, right? Because Ft is a family of sets of size n minus t, we remove the link there. And then because we assume F is large, then this implies F is at most k to the n. Anyway, there's nothing deep going on here. We're just saying if the family is spread, we're done because we assume we can handle spread cases. If it's not spread, then we find a large link and you prove to the link, right? And the only thing we're using here is that if a link contains a sunflower, we can add back the element in the kernel of the link, in T, and get back a sunflower in the original set F. So this definition of a sunflower is inducive to restrict it to a subfamily of all the elements contained in some set T. Okay, so there's nothing deep going on here. Anyways, the whole point is from now on, we can just focus on the structure of spread families. Okay. Yes? How do you know that?
How do we know that link Ft is also K-spread?
So there's two ways you can do it. One way you can do it is look at the maxima link when you have that, and then you can verify its spread. The other option, which is even easier, is let's just apply this lemma inductively on n. Because we assume this is true not just for n, but for every n parameter is smaller than n. Just apply it inductively. So both would work. Yeah. Good question. Any more questions? Okay. So now it's going to be, again, let me keep this definition of spread here for a second, and let me sort of tell you what are we going to prove. So really, our main goal from now on is going to be to investigate the structure of spread families. And again, the way I want you to think about it is that spread families are some model of pseudo-randomness. It is a family of sets that we're saying no element is too popular, and no pair is too popular, and no three are too popular, and so on. And the way we quantify it is that we have this exponential rate of decaying. How many sets contain a single element, or two elements, or three elements, and so on. So that's going to be a notion. By the way, if you look at papers in this area, so there's some papers use K as the spreadness, some would use 1 over K as a spreadness. And there's no consistency here, so that whether it's a parameter is less than 1 or more than 1, we'll let you know if it's this or, it's the same definition, just whether use K or 1 over K. Anyways, I prefer this definition, but of course the same. So here's going to be, so basically what we're going to prove is that if a family is spread, it has the following interesting property. If I choose a small random set, it's going to, with high probability, contain one of the sets in the family. And the intuition that because this family is spread, it's sort of all over the place, so each individual set is maybe very unlikely to be contained in my random set. But because I have so many of them and sort of all over the place, they're basically uncorrelated, and with high probability, at least one of them is going to be contained. That's going to be the main thing that we're going to prove about spread families. So let's make some definitions on that. So let U be our universe, meaning the ground set for all our sets. So let's make a definition. And so the p-bias distribution that I'm going to denote by, if I sample W from this distribution binomial UP, all I mean is that each element, each X in U is included in W independently with probability P. Right? This is like a GNP model, right? You have a family, and we include each element independently with probability P. So I'm going to denote this by bin UP, like binomial UP. Okay. And here's going to be the main tool, allowing us to understand the structure of spread families. Let me just write this here. So this is what's going to be called the spread lemma.
Sorry,
Yes.
what is the definition? It's just the definition of binomial?
It's a distribution.
Yeah.
So it's called the p-bias distribution. It's a distribution of a subset of the universe where every element is included independently with probability P. Because it's just a distribution.
Okay. So
Okay.
it's the same as a p random subset of U?
Yes.
Okay.
Yes, exactly the same. Yeah. Yeah, the thing has many different names.
Yeah.
Yes, thank you. Yeah, I would call it a p-bias distribution or a p-bias set. It's the same thing. Okay, so here's the spread lemma. The spread lemma is going to say that if this spreadness parameter is large enough, then a p-biased set is going to contain one of my sets in a family with high probability. So but this is a way that we'll demonstrate that the set has this random-looking behavior. So let F be a family of n sets. Choose P to be some parameter for p-bias distribution, and assume F is K spread for K being some constant P inverse log, let's do it now, log n. Okay. So the parameter scales like P inverse, but for reasons that you'll see later, we need this extra log n factor. Then the probability, if I sample W from this p-bias distribution, that there exists some set in my family that is completely contained inside my random set is at least a half. Okay? So that's going to be the main tool that we're going to use. Okay, so again, let me repeat this lemma. That's going to be the main technical lemma here. Take any family of n sets that is spread enough. Choose a p-random set with high probability it's going to contain one of your sets in a family. And the parameters are that if I want to get a probability of a half here, I need log n. And in fact, let me already say here that if you want to get 1 minus epsilon instead of 1, you just need to pay here another log n over epsilon. We're going to first see the version of epsilon being a half, and then we can sort of generalize to general epsilon. But that will be the most general version. Okay? So this is what we're going to prove tomorrow. So the goal of tomorrow is to prove this lemma. For the remainder of the time today, what I want to show is how to use this lemma to complete our proof of the sunflower improved bounds. Okay. Yes?
So to be clear, you said that this pseudo-random family, we're guaranteed that there's some set in the family which is contained in W? Or
Yes.
contains W?
Contained inside W. So think of the sets in your family that's been pretty small, of size n, and the universe is very large. Okay? And so, for example, just to get some, let's just get some intuition, right? So let me get some intuition before we're going to see some more technical details. Let's get some intuition. So if F is a family of n sets, which is K spread. So first I'm claiming that such a set must be somewhat large, size at least K to the n. Why? Because just look on the link of a set of size n, and just use the definition of spread. So this will show this family is somewhat large. But of course, being very large doesn't mean that you're random looking. Now, for a single set, for a single, S in F, if I ask what's the probability that S is contained in this P random set when W is sampled from binomial UP, well, this is n elements. Each element is included probability P. So this is going to be P to the n. So this is going to be extremely small. So if we just do an expectation, like a first order, so the expected number of sets in F that are contained in W, expectation over W, is going to be, well, the size of F times P to the n. So if I have any chance of this being at least 1, I'll need the size of the family to be at least 1 over P to the n. Right? Otherwise, there's no chance. And you see, K scales like 1 over P, so we're fine. And we have this extra log factor that we'll see later why we need it. And really what this tells us is this family is this random looking family, K spread family, and K is chosen slightly more than P, then not only the expectation is going to be large, but with high probability, one of these events is going to happen. So they are sort of somewhat uncorrelated to each other. Okay, that's the main benefit we get from that. Of course, otherwise, if you make no assumptions about the structure of the family, it could be that all of the sets contain the same, n over 2 elements, and if they don't happen to lie inside W, then you're done, right? So you need to make some pseudo-random assumption if you're hoping to prove that a random set contains one of your sets with high probability. You need something like that. Okay. So hopefully now it's a bit more intuition. And now I want to show you how we can use this spread lemma towards completing our proof of this improved bound for sunflowers. And really what we're going to prove here is that spread families contain many disjoint sets. So if you remember in the proof of the sunflower lemma, we proved that if every element is very unpopular, 1 over K unpopular, and K is chosen small enough, like R minus 1 times N, then my family contains many pairwise disjoint sets, R pairwise disjoint sets. What we're going to prove now is that your family is spread, and your parameter could be much better than what we saw before, then it is still guaranteed to contain R pairwise disjoint sets. So we can basically get the same proof structure, but with improved parameters. So let me sort of now write this lemma. So let F be a family of n sets. And let's assume F is K spread, where K is some constant R log n. Then F contains R pairwise disjoint sets. So again, the parameter here of popularity is R log n, whereas if you look on single elements, it scales like Rn. So the main benefit here is by assuming spreadness, we could improve the dependence on n from n to log n. And in fact, this is tight. So one of the problems is going to prove is the homework going to show that this is in fact tight. Even if you just want to find 2 pairwise disjoint sets, you need to pay this price of log n. So it's going to be so let's prove this lemma. And this lemma is just going to be a direct corollary of this spread. Let me keep this spread lemma here, and let's prove this. Okay. So randomly color, or let's say randomly partition the universe U into 2R disjoint sets. W1 up to W2R. So just take a random coloring of my universe with 2R colors, or equivalently a random partition into 2R sets where every element goes to one of these sets uniformly. Okay? Notice, by the way, that each individual set is distributed binomially U with probability P, which is 1 over 2R. Right? This will be the marginal distribution of each set. Right? Because every element belongs to a set, it's probably 1 over 2R. And let's define the following event. EI is going to be the event that there exists some set in my family that is completely inside WI. Okay? So I'm claiming that now I'm going to apply, right, this will be the event. That if we, that this, again, you can think about this random color in 2R colors. This says that, color I, there is a set in my family that is monochromatic with color I. And I'm claiming that now the spread lemma tells us that the probability of each individual EI is at least a half. Why? Let's see why. So if you want to get a half here, we need to the spreadness to be some constant, P inverse log n. And this is how we chose K. So again, our P is like 1 over 2R, so P inverse is 2R. So there'll be some constant, 2R, just go to the constant, times log n. This is how we chose the spreadness here. So the spreadness is large enough, so this event happens with high probability. For every color I, there is an I monochromatic set in the family with probability at least a half. So now if we just divide, let's say X to be the sum of these indicators for EI, then the expected value, which just counts how many sets do you have that are like 1 monochromatic, 2 monochromatic, 3 monochromatic, and so on. Like for each one of these events, like how many of these events are happening. So this expectation of X is at least, the number of sets, 2R, times the probability of each one is happening, a half, which is R. So an expectation for a random coloring, there exist R colors, and for each color, there exists a set that is completely monochromatic with this color. But then we just found R disjoint sets, right? Because of course, if two sets are monochromatic with different colors, they have to be disjoint. Let me just write this down so it's clear. So fix some choice of W1 up to W2R, where X is at least R, or this event is happening, because the expectation is happening, so some event makes it happen, but at least R. So that is, there are R colors, I1 up to IR, and R sets, S1 up to SR in the family, where SI is completely inside W of, let's say, Sj, you have Wij. So the set J is getting the jth color. But if this is a partition, so if two sets get different colors, they have to be disjoint. So this means that S1 up to SR are disjoint. And we found what we're trying to find, right? So again, the argument here is how do we find pairwise disjoint sets? We take a random coloring with slightly more than R colors, 2R colors. We're using the spread lemma to prove that each color class with good probability contains some set in the family. We're using an expectation, linear expectation, so that with positive probability, there are many, this happens for many sets. And then this gives us a coloring, and under this coloring, you get many monochromatic sets of different colors, so they have to be disjoint. Okay? This finishes this proof, right? And of course, this completes our proof of the sunflower lemma, this improved bound for sunflower. Of course, modulo that is now to prove this spread lemma. That's going to be our goal for tomorrow. So I want to first see if you have any questions on that, because then I want to move to a slightly related topic. But So are there any questions about anything I presented so far today? Okay. So the last thing I want to tell you about is we can use this notion of spreadness to actually define another type of sunflower called robust sunflowers, for which many of the things we're doing here are tight. So for sunflowers, we don't know if what we can prove is tight, but for robust sunflowers, we can prove the things are tight. So let's define it. So then before I define, I'll give you an intuition. So remember that sunflower is you have some kernel, and then you have some disjoint sets around this kernel. The way we're going to try to robustify, say, well, let's now have a kernel, same as before, but now we're going to have many, many sets that might overlap, but they don't overlap too much. So I want to say there's a kernel in all the sets, and otherwise they're mostly disjoint in some specific way. And the way they're going to do it is going to be related to this spread lemma and to the probability of a random set to contain something. So let's make a definition here. So let F be a family of sets. We say F is P epsilon robust sunflower okay, so this is what we define here. So here P and epsilon are two parameters between 0 and 1. If the following thing holds. First, we're going to say, let's take the intersection of all the sets in the family. Okay, similar to a sunflower. There might be some non-trivial intersection of all of them. First thing we're going to require this intersection is not in our family. Okay, that's going to be one restriction that we need here. And the other one they're going to say is, except for this, there are mostly disjoints. And the way we're going to quantify this as follows. If I choose a random p-biased set, and with high probability, the probability is set in my family such that it is inside W, but without the kernel. So the kernel I'm going to give for free, but except for the kernel, I want the other parts to be inside W. So that S is inside K union W. I want this to be at least 1 minus epsilon. Okay? So again, so let's see. Let's try to get some intuition around this definition. So what are we saying? So we have this set family that might be now very large, and K is the common intersection of all the sets. So this we're saying this you get for free, but I want that with high probability a p-random set is going to contain some of the petals, like when we remove this common intersection, which equivalently say that my set is inside this random set union with the kernel. The kernel you get for free. Okay? So this will be a notion of a robust sunflower. And this notion actually came up initially by Ben Rossmann when he was using it to prove lower bounds in circuit complexity. Since then, this notion and related notions have become very useful for proving lower bounds on monotone circuits. So in fact, on Friday, we're going to see how to use this notion to prove a lower bound on monotone circuit complexity for some functions. So this, you're going to see how this is going to get applied in CS on Friday. For now, let me tell you that we can basically use the spread lemma. So we know that for sunflowers, we had this bound, right? So remember that for sunflowers, what we can prove now is that sunflower NR is at most some constant, right? R log n to the n. That's the best one we know how to prove today. And turns out we can prove something very similar for robust sunflowers. And so I'll tell you the bound here. So the bound that you can prove, so here's a theorem. It says that, if F is a family of n sets, which is P epsilon spread, then we can also bound its size by some constant, P inverse log n over epsilon to the n. So I believe this theorem is going to be one of your exercises for the problem set. And the proof of it is, again, going to be exactly, so the spread lemma is going to be your heavy tool machine we're going to use here. So we're going to use a spread lemma plus induction on links, like we've done for the sunflower case, right? So either there a link that's popular or not. And based on that, you can prove this. So, yes?
Did we define what is P epsilon spread?
Yes, we did. Oh, sorry, P epsilon, sorry. I think maybe, sorry, I did not want to do that. You're right, I did not define it. Family of n sets. It's related, but I think I defined it slightly differently. Sorry, let it be a family of n sets without, you're right, without a P epsilon, thank you, a robust sunflower. Then, thank you. I'll comment on this as F constant P inverse log n over epsilon to the n. Sorry, thank you. So P epsilon spread is just something I'm not going to define here. It's basically a P epsilon robust sunflower with an empty intersection, but the kernel is empty, which also comes up in applications sometimes, but we won't need it here. So let me not go into that. So again, so this is a notion of a sunflower somewhat similar to the usual notion. And I'm claiming we can use a spread lemma basically to prove the theorem. Say that if a set is too large, it must contain a robust sunflower. So this is one theorem you can prove. But then you can ask, like, how is this notion of a robust sunflower related to a sunflower? So it's going to become our second theorem that says that, P, which is 1 over 2r, epsilon, which is a half, robust sunflower contains an R sunflower. Okay? So again, what I was saying here, if you have a robust sunflower with good enough parameters, meaning your P is something like 1 over R, it's actually 1 over 2R, epsilon is a constant, a half, this contains a sunflower. So actually, both of the theorems are going to be part of your problems. No? Which one? Just the second one. OK. So the first one I might prove today. We'll see. We'll see how much time we have. So OK. Second one, OK. Let's say something about both of them. The second one is basically in the same way we prove that, if a family is a is K-spread, K is large enough, it contains R disjoint sets. You can use exactly the same proof to show that if you have a robust sunflower, then it contains a R sunflower. And the way you do it, well, if the kernel is empty, it's exactly the same thing. If the kernel is not empty, you remove the kernel and then you apply it. So that's going to be a nice exercise for you to do in the problem set. This one is also following the same type of machinery, but I think Anthony is reminding me that I actually plan to talk about it today. So let me see how much time I have here, and then based on that, I'll decide. Oh, we have another 11 minutes. OK. So let me just sort of say in words how you would prove the theorem, because I want to spend the last few minutes talking about something else. So I would say, you want that the family does not contain, if the family is too large, it must contain the P epsilon robust sunflower. So the way you would say that, well, if the family is spread, then we can basically use this spread lemma to prove that it contains, I think maybe I do want to show you something. Okay. Now, actually, let's spend a few minutes talking about this theorem. Okay, so let's prove the theorem. So let me use K, our spreadness parameter, to be exactly this thing here. This constant P inverse log of n over epsilon. And there are going to be two cases. So we're assuming that the side of f is at least k to the n, right? And I want to prove that this contains a robust sunflower. So the first step is we're going to move to a link that's going to be k-spread. Originally, we don't know that the family is k-spread. We just know it's large enough. So the first move is going to be, let's move to a link, and inside this link, we can guarantee your k-spread. So let T be maximal such that Ft is at least the side of f over k to the t. Okay? Let's show this maximal link. So I'm claiming, first of all, this link exists because they could choose T to be empty. Right? So this exists. Also, I'm claiming that the side of T, so T is at least 0. I'm claiming it's also less than n. I cannot go to like a full set, because if I went to a full set, I'll just get exactly the side, I mean, with the side of f, we assume is more than k to the n. So if I choose T to be a single set in my family of size n, then I'm going to lose f over k to the n, and it should be 1. So that's not going to work. So T is some set between empty and less than full. So in particular, this implies that T is not in our family. And I'm claiming that Ft now is k-spread. Why is it k-spread? Well, let's see. If it was not k-spread, because if not, then there will exist some R, disjoint from T, not empty, such that Ft R is more than Ft to the k to the R, right? This would be the definition of not being spread. There is a link that's too big. But if there is a link that's too big, then T cannot be maximal. You could have replaced T with T union R. Because going to a T link, and inside that going to an R link, is the same as originally going to T union R as a link. So we get this link, and this link is now going to be k-spread. Now, again, we can use our spread lemma and say, well, if my link is k-spread, right, now we have a link, T. The link is k-spread. So the spread lemma tells us that the probability over W binomial UP that there exists a set in Ft inside, S is inside W, is at least 1 minus epsilon. Right? This is, again, we're applying the spread lemma, saying if you have this spread as property, then a random set contains one of a set with high probability. But I'm claiming that this is exactly the definition. This is the same as saying that Ft is a P epsilon robust sunflower with empty intersection K, right? I mean, we don't really need the second part. This is just something that we get for free. So again, the definition of P epsilon robust sunflower said, if you remove the common intersection, then you exactly get this. And here we get it even without removing anything. So in particular, it is a robust sunflower. This is just the definition of a robust sunflower. But this means that if I take, if I add back T, if I now define F prime to be, take S union T for all the sets in this link, that this is inside F. And again, by definition, this is a P epsilon robust sunflower. So the definition of robust sunflower said that, you remove the common intersection, in this case it's T, and now it becomes this has this property that a random set contains a probability. So everything is just going around definitions. There's nothing really deep going on here. So the only heavy machinery we're using here is this spread lemma. right? So I think this will be good for you to maybe try to go through the proof again, in the problem set, because this is all about understanding the definitions here. Again, like I said, there's nothing too deep going on. So I think in my remaining, 4 minutes, I want to tell you why for this notion of spread lemma, or why for these robust sunflowers, we need to pay this log n factor. So people who do random graph theory, in random graph theory, you need sometimes to pay these log n factors, and we're going to see that come up on Thursday. Here I want to show you a more basic reason for that. So I think here's going to be another example. It's going to be a very similar example to the one we've seen yesterday. So think about the following universe. You have n here. You have some parameter k here. These are my rows. And my families are going to be all the sets containing one element in each row. Okay, so formally I have rows R1 up to Rn. So each one of them is of size k, and they are disjoint. And my family is going to be all the sets, such that for every I, S intersected Ri has size 1. So I'm claiming two things about this. I'm going to choose the parameter k in a second. So I'm claiming, first of all, F is k spread. Why is this family k spread? Let's see. Let's say we take a single element here. This is exactly 1 over k fraction of the sets, right, by definition. What if I take 2 elements? Well, if they're in the same row, then the probability is 0. If they're in different rows, it's 1 over k squared, and so on. So this is so if we just verify this is k spread. And now I'm going to say, well, if I'm going to choose k to be some constant log n, so small enough constant log n, then I'm claiming that if I choose, let's say, even w to be binary, even with 1/2, a random set, the probability that there exists a set in a family inside w is going to be very small. Let's say it's less than 1/2. And you can, of course, play with the constants. So why is this although this is like a spread family, it's going to be unlikely that a random set contains a set in a family. And the reason is going to be because a random set with high probability is going to completely miss one of the rows, right? The probability, this is because with high probability, there exists a row Ri that is disjoint from W, right? I choose a random set, let's say probability half each element, and the rows are of length, I don't know, 0.1 times log n. You could do the calculation and see that with very high probability, one row is completely missed. And of course, if one row is completely missed, I cannot contain any set in my family. And again, you can play here by playing with these parameters of k. You can boost this to epsilon. You can boost this to p. You can play with other parameters. So this type of example shows that everything that we're doing here is tight. I mean, if you're trying to prove this, if you want to prove the spread lemma, you need to pay this log n over epsilon. And in fact, you need to pay exactly this up to the constant by, again, setting this to be k here. And also, if you want to get disjoint sets, that's maybe not obvious, you can modify this example a little bit and get an intersecting family that it is still very spread and, it's intersected. So you cannot even find 2 disjoint sets. So that, again, is going to be one of your problems in the problem set. So by modification of this example, it shows the tightness of this approach in many different ways. So I think so here, just as a summary, if your goal is to get to prove the sunflower conjecture, this is the limit of this technique. So it goes a lot of the way, but not we can prove this cannot get us all the way. But for many applications, in particular in CS, it turns out that this notion of robust sunflowers is a much more useful notion than the notion of a sunflower. And then, we pay this log n, but we have to, and it's fine. And okay, so that's it for today. And again, our goal for tomorrow is, again, I'm going to remind you the definitions. And tomorrow, we're going to see a complete proof of this spread lemma. Okay, so that's it.